In this video, I'll show you how to use an accelerometer with an Arduino. If you've ever played a video game with motion controls or noticed how your phone can automatically rotate the screen when you tilt the phone from vertical to horizontal, then you've used an accelerometer without even realizing it. The nice thing about an Arduino is it lets you take the signal from the accelerometer and program it to control whatever you want, for example, this motor. Let's zoom in and take a closer look at the accelerometer itself. Now, the accelerometer I will be using as a demonstration in this video is the ADXL355, which is an analog accelerometer, meaning it outputs separate voltages for acceleration in the X, Y, and Z directions, and you can see those directions labeled on the board here with the circle indicating that the Z axis is perpendicular to the surface of the board. So positive X is that way, positive Y is that way, positive Z is up. This is a breakout board for the accelerometer made by SparkFun Electronics. So the accelerometer itself is this little black chip here, but it is soldered on to this circuit board, which then has header pins where I can connect jumper wires to connect to my Arduino. And you see those pins are labeled VCC for power, GND for ground, and then X, Y, and Z for the three different acceleration voltages, and then an ST pin, which we are not using. So many of the concepts I'm going to talk about in this video will apply to other types of accelerometers, but the wiring and code I'm going to use are specific to this one. So if you are using a different accelerometer or a digital accelerometer, which uses a communication protocol different from just outputting three analog voltages for the three accelerations, you may need to change your wiring diagram in your code. But again, what we're going to talk about shortly, conceptually explaining how accelerometers work, is going to apply to any accelerometer. Now, if we look at the Arduino end of this, remember that our accelerometer had 5 wires, so I have color-coded them here: black for ground, red for power. The ADXL355 is powered by 3.3 volts, so it is important to read your accelerometer's datasheet and find the acceptable range for power supply voltage. You do not want to damage it by powering it with a voltage that is too high. So if you're used to working with the Arduino ecosystem where many things are 5 volts, in this case I'm going to use the 3.3 volt pin to power the accelerometer. I could damage it if I plug that wire into 5 volts. And then I have my 3 acceleration voltages, X, Y, and Z, which I'm going to plug into the Arduino analog in pins A0, A1, and A2. And then, as you'll see when we go to read the code, I'll be able to use the Arduino's analog read function to get the voltages on those pins. Let's switch over to the computer and look at the code that I'm going to use just to read those 3 voltages. So if you have done anything with the Arduino analog read command before, this should be pretty similar. We are just doing it 3 times. If you are new to Arduino, you might want to go to the link in the description and check out our Arduino tutorial playlist, where we use this with a potentiometer just on a single pin to explain how the analog input works. But to do it for all 3 accelerations, I'm just going to declare 3 variables. I'm going to call AX, AY, and AZ for the 3 different axes, but you could call them whatever you want. In my setup function, I am going to initialize serial communication, and then in my loop function, I am going to use 3 analog read commands to read those 3 analog pins, A0, A1, and A2, and then I'm just going to print out the 3 values to the serial monitor. So let's take a look at what happens when I do that and then move the accelerometer around. So as you can see here, I have the accelerometer sitting flat on the table, and I have the 3 acceleration values printing out in the serial monitor, X, Y, Z. And when the accelerometer is not moving, those values are around 330-ish, 320 for X and Y, and then about 400 for Z. And we'll talk more about the units later, but again, if you go back to a tutorial about Arduino analog read function, this is a value between 0 and 1023, which is related to how the Arduino converts an external analog voltage to a digital number that your code can work with. But the units of this number are not volts, and they're not meters per second squared, if you're familiar with acceleration from physics. So we're going to need to convert that later if we want to get the actual voltage or the actual acceleration in meters per second squared. But for now, we're just going to look at how these numbers change when I move the accelerometer around. So remember, you probably can't see the little labels, but the X direction is this way on the accelerometer. So if I shake it in the x direction, it's happening really fast, but you can kind of see how that x number changes more than the y and z numbers. And the other interesting thing you'll note here is if I tilt the accelerometer, so I'm not shaking it, I'm not moving it side to side, but if I tilt it, so the direction of the x-axis is changing relative to gravity. So here, the x-axis is flat, the x-acceleration is reading about 330. If I tilt it this way, that x-acceleration goes down to around 270. And if I tilt it the other way, it goes up to around 400. So it seems like our accelerometer is not just being influenced by linear motion, or what you would consider acceleration if you've taken a physics class. It's also being influenced by the direction of gravity relative to which way the accelerometer is pointing. And to understand that, we need to talk about the physics of how an accelerometer actually works. To explain how this works, I want you to imagine that we have a spring like a slinky, and that sling is suspended from one end. So you're holding it, or it's tied to the ceiling or something. That's what this little symbol here represents. And then we hang a mass or a weight from the other end. So assuming we're on Earth and there's gravity, gravity is going to pull down on that mass, and the spring is going to stretch out. So it will be longer than its resting length. If we just laid the spring horizontally, so gravity wasn't pulling it down, it would have some original length. We'll call that length L, and then it's going to stretch out to some length longer than L under gravity. And what an accelerometer effectively does is it can measure this stretch, how much the spring has stretched, and that tells you how strong gravity is, or how much it's pulling on the mass. We're not going to get into the details of how exactly it measures that electronically and converts that stretch into a voltage. There's more detail than we're going to go into in this video. The important thing to understand for our purposes is that we can also imagine if we put the spring horizontally, but used it, for example, to pull a little toy car or a mass on wheels. So we attach the spring to the car on one end, and then we grab the other end of the spring and we accelerate it, or we pull on it. Sorry, that looks like a 9, but that should be an A to represent acceleration. We pull on it with an increasing velocity, so not a constant velocity, but we grab this end and we yank it. We keep going faster and faster. That is also going to cause the spring to stretch out as we pull, even though there's no gravity in the horizontal direction. We are just pulling on this mass. So an accelerometer can still measure that stretch, or that change in length, which I'll indicate with a Greek letter delta to mean change, delta L. In both of these cases, the accelerometer can measure delta L, or it knows that the spring is stretched, but it doesn't know the orientation. It can't tell the difference. All the accelerometer knows is that the spring has changed length. It does not know if that change in length is due to horizontal, linear, or acceleration, or due to holding still vertically but gravity pulling down on the mass. The accelerometer on its own does not know whether it's pointing up or down. Again, sorry if I'm repeating this, but I really want to drive this point home. All the accelerometer knows is that the spring has changed length. This is a common thought experiment in a physics class where if you imagine yourself in a windowless rocket or elevator, standing there with no windows, so you can't see outside, you can't tell if you're moving. If you feel an acceleration, so you can feel either the floor pushing up on your feet or yourself being pulled down on the floor, technically you cannot tell whether that is because there is a downward pull of gravity and you are just sitting still on the surface of Earth, or if you are in space and accelerating forward at the same rate. So acceleration due to gravity on Earth is 9.81 meters per second squared, if you've taken a physics class and learned about the units. So you can't tell if you're in Earth's gravitational field or if you are accelerating upward at 9.81 meters per second squared. As far as the human body is concerned, if you're just standing in that windowless elevator and you can't see outside, so you don't know if you're moving, there's no external reference, all you can feel is the floor pressing against your feet, then again, you can't tell whether you're accelerating upward or if you're just holding still in the presence of gravity, and it's the same thing with the accelerometer. So that is why if we take our little accelerometer with its X, Y, and Z axes, again with Z pointing out of the screen here, and I shake or accelerate the accelerometer left and right, or I take it and I rotate it so the direction of the x-axis has changed relative to gravity, with gravity pointed down, both of those motions are going to result in a changing voltage, and that's what we were seeing on the serial monitor earlier. So when you are using an accelerometer in an Arduino project, you need to think about which of these motions are physically possible and which one you're measuring. For example, if you are mounting your accelerometer on a wheeled robot that can drive around, but it's driving on flat ground, then you know that this isn't going to tilt, so you're measuring linear acceleration and not rotation or tilt relative to gravity. But if you are doing something with a handheld game controller and you tell the person, okay, this controller is designed to be tilted, but don't shake it side to side, then you know that ideally you are measuring rotation and not linear acceleration. Conversely, if you put it on something like a drone or a quadcopter, you have your accelerometer on there. The drone is free to move around in space, so you could be measuring rotation relative to gravity or linear acceleration. And that is why drones use additional sensors like gyroscopes, which can measure the rate of angular rotation, and magnetometers, which are sort of like a three-dimensional compass that can measure the orientation in space relative to Earth's magnetic field. When you combine all three of those sensors, you get something called an inertial measurement unit that does a better job overall differentiating between these linear accelerations and rotations. But those are really topics for a different video. We're not going to get into gyroscopes and magnetometers here. We are going to circle back and just focus on the accelerometer, and now go back to those unit conversions and look at the accelerometer datasheet to understand how we get from that raw number in the serial monitor to an actual acceleration, either in Gs or meters per second squared. So going back to the serial monitor, as a reminder, we have the raw X, Y, and Z analog read values printing out here, and you can see them changing as I tilt and move the accelerometer around off camera. But this is just a number between 0 and 1023 coming from the analog to digital conversion the Arduino is doing with the analog read function. To get it in actual units of acceleration, so either Gs or meters per second squared, we first need to convert this back to voltage, so corresponding to the 0 to 5 volt range on the Arduino's analog input pins, and then convert that voltage to acceleration. To do that, we're going to need to look up some information in the accelerometer's datasheet. So here I have the datasheet for the ADXL335, but again, remember, if you are using a different accelerometer, you are going to need to look up the datasheet for your specific model of accelerometer, which you can usually find through a quick Google search for the part number and the word datasheet. And there is a ton of information in this datasheet. It can be a little overwhelming, but we do not need all of it. I just need two numbers from the table on this page. I need the sensitivity and the bias level. So the sensitivity, which you can see in this row here, you see that it has minimum, typical, and maximum values. We are going to use the typical value, which is 300, and then it gives us units over here of millivolts per G. So what that tells us is that for every 1 G change in acceleration, the accelerometer's output voltage is going to change by 300 millivolts. So it has a sensitivity of 300 millivolts per G. The other thing we need here is the bias level, which tells us what the output voltage is when the acceleration is 0 G. So the output voltage is not 0 when the acceleration is 0. The output voltage is 1.5, and this is because the accelerometer only outputs positive voltages. It doesn't output a negative voltage for a negative acceleration. The whole thing is offset. And you need that because the Arduino's analog input pins also only accept positive voltages. They can measure between 0 and 5 volts. they can't measure between 0 and negative 5 volts. So that is why the entire accelerometer output is biased or offset, so it always outputs a positive voltage. Now here, notice that we have different values for the X and Y axes, and then the Z axis, so they are both centered at 1.5 volts, but then they have different minimum and maximum values with a slightly bigger range for the Z axis. So given that information, how do we convert between voltage and acceleration? We know that we have a sensitivity of 300 millivolts per G, and that G represents 1 G of acceleration, which is 9.81 meters per second squared. So that G does not represent grams. Don't get that mixed up with your other metric units. And we know that we have a bias voltage of 1.5 volts. So one way to visualize this graphically is just to think of this as a line, where if we have acceleration in G on the x-axis and output voltage in millivolts on the y-axis, when acceleration is 0, remember we're not going to have 0 output voltage, we're going to have 1.5 volts, which is 1500 millivolts, and then we're going to have a line going through that with a slope, rise over run, of 300 millivolts per G. So for every 1 G increase in acceleration from 0, the output voltage is going to go up by 300 millivolts. So for example, at 1 G, I'd have 1500 plus 300. That would give me 1800 millivolts, or 1.8 volts. And if I go down to negative 1 G, then I would subtract 300 millivolts, and I would have 1200 millivolts. But again, that doesn't go negative or less than 0. This value is always positive over the range of the accelerometer. And that is something I didn't mention yet, but should have. Every accelerometer is going to have a maximum range that it can measure. So it can't measure infinite acceleration. And that is also information you can find on the datasheet. And in the case of the ADXL 335, that's plus or minus 3 Gs of acceleration. So depending on the range, the accelerometer may saturate or max out its output. So there's a point where the voltage isn't going to get any higher or any lower. So if there's a really sharp impact, or you drop the accelerometer or something with a really high acceleration, it might not be able to measure it, but there are other accelerometers with bigger ranges out there. So we've represented this graphically here, but we would like to get an equation that lets us convert between acceleration and voltage. And you might recognize that this is just a straight line, so we can use the equation of a line, y equals mx plus b, where m is the slope and b is the y-intercept. So in this case, that's going to be the voltage in millivolts is equal to the slope, which is 300 millivolts per G, times the x value, which is that acceleration in G, plus the y-intercept, which is 1500 millivolts. So there, I have an equation where I have my two unknowns, my voltage and my acceleration, and I can either, if I know the acceleration, solve for the voltage, but really what we're going to want to do with the Arduino is the other way around. We know the voltage measured from the Arduino, and we want to use that to solve for the acceleration. So to do that, we could rearrange this equation. First, if you're familiar with algebra, by subtracting 1500 from both sides. So we have the voltage in millivolts minus 1500 millivolts. And then we're going to divide both sides by this 300 millivolts per G, and that is going to be equal to our acceleration in G. So there is our equation to convert a voltage to acceleration, where again, this is the bias or offset, and this is the sensitivity. And the values I'm showing here are specific to the ADXL 335. You need to look up those numbers in the datasheet for your accelerometer if you're using a different one. So that's great, but remember that the Arduino analog read command is not giving us this voltage directly. It is giving us a number between 0 and 1023 corresponding to the range 0 to 5 volts. So we have one more conversion to do first. And again, this is just going to be the equation of a line, where when I have 5 volts, the ADC, or analog to digital converter, is going to give me the number 1023. But in this case, I don't have an offset. The line goes through 0. So when the voltage is 0, the ADC value is also going to report 0. So I have, I'm going to call this my A, I'm going to abbreviate that ADC. And this is my voltage V in volts. I'm going to have voltage in volts just equals my slope, rise over run, which is going to be 5 over 1023. So 5 over 1023 times my ADC value, and then the intercept is 0, so there's no plus intercept there. It's just that. So in my code, I'm going to need to use this equation first. I should note that this is specific to the 5-volt Arduino, assuming you are using the default 5-volt analog reference. There is a command you can use to use a different analog reference voltage with the Arduino, which sometimes is a good idea to use because the 5-volt reference can be noisy, especially if you are powering a lot of other things like lots and lots of LEDs or a motor with your Arduino. This voltage, the actual voltage, can fluctuate. It's not always exactly 5 volts, and then that can affect your ADC reading and the conversion here. But we're not going to worry about that too much in this video. Again, that's really a topic for a different video. We're just going to use the default 5 volts. So there we have these two equations. Let's go take a look at what this looks like in code to convert that analog read value first to a voltage and then ultimately to an acceleration. All right, let's take a look at this in the code. Now, there's a lot going on here. I will walk you through it line by line, but you can also download this code from the link in the video description. So first, I have what I had before when we were just doing the raw ADC readings. I'm going to declare variables for those, but I added the underscore ADC kind of to label the units for my different acceleration variables, because you're going to see I'm going to have different versions of this later. Next, I am going to declare variables for my 3 voltages, and you will note that I declared those as float instead of int. Getting into Arduino variable types is, again, really a topic for another video. The very short story here is that the most common one you see in introductory Arduino tutorials is int, and that means that this variable is going to be an integer, or in other words, it's not going to have any decimal places. Even if you do a calculation like division that results in a decimal place for this variable, that's just going to be truncated or cut off. So 10.2 will just become 10. For the voltages, I want to be more accurate than that. I don't want to lose the decimal places, so I am going to declare them as floats instead of ints. Float is short for floating point, so if you think of the decimal point sort of as a little floating point that can be anywhere in a number. But again, getting into variable types is a topic for a different video. So I have my variables for the voltages there. I am also going to declare variables for that reference voltage and maximum ADC value of 1023 that we talked about earlier. Again, if you're using all the defaults, this is just going to be constant. You could use 5 and 1023 in your equations, but there are ways to change to a different reference voltage in the Arduino, and some models of the Arduino you can actually change the resolution of the analog to digital converter, so you could have a different number here. So having these as variables just makes it easier to change them later, but again, we're just going to stick with those default values. Next, I have my accelerometer parameters that I looked up in the datasheet. So again, remember that if you have a different accelerometer, your numbers are going to be different here. Again, I declared all of these as floats because I want to keep the decimal places. And note that I made my units here volts instead of millivolts. So 0.3 volts per G instead of 300 millivolts per G. And then 1.5 volts instead of 1500 millivolts for all of the bias voltages. I then declare more acceleration variables for the different units. First, I'm going to have the accelerations in G, where again, 1 G or 1 Earth gravity is equal to 9.81 meters per second squared. And finally, I have variables for the acceleration in meters per second squared. I do have a value for Earth gravity here, just in case you were using an accelerometer on Mars or something and wanted to change this to a different number to do that unit conversion later. Our setup function is not going to be any different. All we need here is our serial begin command to initialize serial communication, to print out all of the different variables to the serial monitor. And then in our loop function, we are going to start off the same way we did before. We are going to use 3 analog read commands to get the raw ADC values from the 3 different analog input pins. Next, we are going to convert those raw ADC readings to voltages using the equation we saw earlier. So I have the voltage is equal to my reference voltage value, which remember I set that variable to 5 volts earlier, times the ADC reading, divided by the max ADC value, which is 1023. Once I have that voltage, I can then convert it to acceleration in G using my next formula. I take the voltage, subtract off the bias voltage, and divide it by the sensitivity, which is going to give me the acceleration in G. And finally, if I want to convert that to meters per second squared, I multiply that acceleration in G by my acceleration due to gravity, which on Earth is 9.81 meters per second squared. I now have a whole boatload of variables, 4 different values in each of the 3 axes, so 12 total, and I'm going to print them all out to the serial monitor. One quick note, serial printing is slow, so this will slow your code down significantly. This is useful for debugging or just learning how the accelerometer works. But eventually, when you are using the accelerometer to do something or control an output, like I was doing with the motor at the beginning of this video, you're going to want to comment out all of these serial print lines. And rather than doing that one at a time by typing the / character, you can highlight everything and then go up to the edit menu, which we can't see right now because I have this window full screen. But if I unfull screen it, I can go to edit, comment, uncomment. That will add comments to the whole thing, and then I can go to edit, comment, uncomment again to remove the comments. So now we can upload this new program and look at our giant output in the serial monitor here, where we have, again, the initial ADC value for all 3 axes, the voltages, the acceleration in G, and the acceleration in meters per second squared. And what we would expect when the accelerometer is just sitting flat on the table with the z-axis pointing up, and it is not moving, is that I would read 0g, or 0 meters per second squared in the x and y directions, and 1g, or 9.81 meters per second squared in the z direction. And you will see that that's not what I'm getting. I am registering around 4 meters per second squared in the x and y direction, even though it's not moving or tilting, and 16 meters per second squared in the z direction, which is much higher than Earth gravity. And thanks to the output on my serial monitor here, I can identify the issue. Let's look at these voltages. The X and Y voltages are about 1.64, 1.65 when the accelerometer is sitting perfectly flat. And you may remember, earlier, I set those bias voltages to exactly 1.5 volts, which was the middle or typical value from the datasheet. But the datasheet did give a range. It's not necessarily going to be exactly 1.5 volts. So I need to calibrate my code to the actual zero or bias levels from my accelerometer. So we can see when it's sitting flat, I'm getting about 1.64 in X and Y. And if I tilt it, so the Z-axis is now horizontal instead of vertical, and try to hold this perfectly flat, I'm getting about 1.69, 1.7 in Z. So what I'm going to do is go ahead and change these values. So I'm going to enter 1.64 for X and Y, and 1.69 for the Z bias voltage, re-upload this code. And now, as the accelerometer is sitting flat, we see that I'm not getting perfect exact zero values, but I am much closer to 0 in X and Y, only off by about 1/100th of a G there. And again, the accelerations in meters per second squared are very close to 0. The Z direction isn't perfect. I'm reading a little over a G, and about a little over 10 meters per second squared instead of 9 point something. So again, it's never going to be perfect. There's always going to be a little bit of noise, and I'm never going to hold this perfectly flat. But for example, if I tilt it 90 degrees so it's sideways now, then I am now reading about 0 in the z direction and about -1g or -10 meters per second squared in the x direction. So we haven't really talked about sign convention so far, but you see that depending on which way I rotate this and whether the positive direction for the axis is pointing up or down determines whether the resulting acceleration is measured as positive or negative. But so I could go back and tweak these calibration values again, maybe try 1.65 instead of 1.64 to see if I can get that closer to 0. But that is a dramatic improvement over just using the default value in the datasheet. So you now know how to read the accelerometer values into the Arduino, what physical motions can cause those values to change, whether they are linear accelerations with no rotation, or just rotations relative to the direction of gravity with no linear acceleration, and you know how to convert those or get them in 4 different units or values. You have the raw ADC value, the voltage, the acceleration in Gs, and the acceleration in meters per second squared. Once you have these numbers, you can do anything you want with them. This is the great thing about the Arduino. So if you want to use it to control a servo motor, like I showed at the beginning of this video, you can do that with the servo library by mapping these numbers to the angle of the servo, but you could use them to control LEDs or any other output that you can connect to an Arduino. So rather than showing you how to do all of those possible options in this video, we are going to refer you to our Arduino tutorial playlist linked in the description, which covers things like LCDs, LCD screens, and LEDs and motors, and all of the other outputs you can use. If you're looking for a project you can do with an Arduino, like building a robot or an automatic watering system or an automatic pet feeder, or tons of other cool robotics and home automation projects you can do for a school or home project, check out our website, www.sciencebuddies.org, where we also have over 1,000 other projects in all areas of science and engineering.